Hi everybody, my name is Hyun-Joong Kim from Seoul National University, Republic of Korea. It is regrettable that the 9th International Scientific Conference Wood and Fire Safety 2020 will be held or WFS 2020 online web year due to coronavirus pandemic. Thank you very much for inviting me for the WFS 2020 as a keynote speaker. Today, the title of my talk is Fabrication and Characterization of Flame-Retardant Nano-Composites. It's an introduction, nanomaterials, intermotion agent, flame retardants, and conclusion. First part is introduction. As you know, our life was surrounded by polymeric materials. For example, automobile interior materials and building materials, interior materials for airframe. 4,000 killed and 80,000 injured every year in EU. And also so many people deaths annually worldwide. And also cost average 1% of GDP in EU. Halogenated fire retardants release gases which are toxic, corrosive, and damage the ozone layer. Still much to do is regard to surface sprays of flame and the generation of smoke, particularly for the transport sector. As you know, damage of human life in flame is over before flashover, which drives the Great Fire. Delayed flashover time with flame retardants can be enhance the fire safety and save the human life. For make good flammability, halogen-containing agents was used before, and also they showing good flammability performance. WHO and US EPA recommends a limit on the exposure amount for the risk assessments of toxic components. Reason why we start about halogen-free flame retardant. So, how to replace the halogenated flame retardants? I can explain 3 types. First part is metal oxide powder. Second part is phosphorus-based incandescent flame retardants. Finally, that is third, nanomaterials. For example, nanoclay and carbon nanoparticles. Many flame retardant systems were designed and investigated. So I will explain more detail. First part, metal hydroxide. It is usually requires higher loading in polymers of up to more than 60%. Because the flame retardant mechanism is based on the release of water. It is stable up to temperature of around 300 degrees. Second part is phosphorus-based intermittent flame retardant. It is introduced into the polymer materials. Their mechanical properties will sharply decrease. Finally, third part is carbon-based materials. It must be treated with strong acid like sulfonic or nitric acid to get the expandable materials, which is mixable with organic polymer. Second part is nanomaterials. Nanoclays are classified depending on their element composite and dimension. That is one of the example of nanoclay. The formation and the size. And so many people working for the nanoclays, that is like this. And nano-composite formation, sometimes immiscible system, sometimes intercalated, sometimes exfoliated. Each conformation is the intensity, the X-ray scattering is so different. So that is important. So when the nanoclay is used in a composite as a flame retardants nanometallic additives, dispersion is very important factor to accomplish the flame retardant property. And the third party intumescent agent. An intumescent is a substance that swells as a result of heat exposure, thus increasing in volume and decreasing in density. As you can see the figure, after being subjected to fire, typically filling expansion is over 50 times. Using these materials can make other type of intumescent chemical components. For example, 3 type APP, PER, MA. So that is we synthesize of polyphosphodiamino-diphenyl methane spirocyclic pentaerythritol bisphenol phosphate. We called PDSPB. And finally, the flame retardant. The composite material is added FR, shrinkage of the residue is not observed. However, in the case of the clay materials is added and observed that residue is contracted. Then, when clay is added and confirmed that mass of residue is more produced, you can see the figure, pure EVA and EVA with FR 10% and the nanoclay 0, and that is EVA and the FR 0, nanoclay 10%, and finally EVA FR 5%, including nanoclay 5%. So you can easily understand using of the HR peak. So calorimeter experiments, heat release rate, we call the HRR, time-dependent curves, comparison of the efficiency about same rate of additives, different composition. Flame retardants, nanoclays, retardant clays. So HRR decreases to adding clay. So we can control the nanoclay. It should be HRR is decreased. So observing about the residue, in the case of the clay materials added, I have observed that the residue is contracted. Then, when clay is added, we have confirmed that the mass of residue is more produced. The mechanism of clay silicate layer distance change by clay and the intumescent system reaction during consumption. Reason why the difference of the XR peak 13.8 angstrom occurs is while the cetyl methyl ammonium surfactants is present between the layers of clay. APP was added as intumescent agent, acts as an electronic hydrogen inhibitor, interrupting the breakdown of the cetyl methyl ammonium. As a result of the single carbon layer is believed to be generated between the silicate layers. So you can see the figure 21.4 angstrom between the clay. That is a reaction with the high temperature of 800 degrees, and then change into the 13.8. So between the clays contracted each other. Conclusion: flammability has many complicated reasons, including chemical properties and the physical properties originating from the morphology, and when additives are used together, they can have a synergetic outcome. So main issue of entering new age, and we can convert into core compositions. Thank you for well-organized WFS 2020 online webinar. Thank you very much for your attention.